So this time we're getting a bit more complicated, but the principles all stay the same. But what I've done this time is I've added on a little pure moment or a couple. So I've added that on, 3 kilonewton meters. We've also got a force going, well, we've got an applied force going up the way. I don't know how that might be. That might be an internal support or something like that. Maybe, I don't know, but something's applying a force up the way. Or maybe it's getting hung from a cable up here, something like that. And we've got a few more forces just to get a bit of a more complicated shear force diagram. So always the first step is to find the support reactions. So I'll quickly fly through that, and then I'll just draw some sections for us to think about what's going on here. But then we'll probably draw the shear force diagram just using those simple rules where you just follow the forces and keep constant in between. Sorry, I got a bit of a cold, so I'm going to be coughing and spluttering through this one, but we'll push on. Okay, so I found those reaction forces. What I did was I just stuffed around with this a bit more. I've just changed it to make it a bit more interesting and to make the numbers come out a bit tidier. So I changed this moment to 10 Newton meters. Better make that 10 kilonewton meters. 10 kilonewton meters. So just work through. So the sum of the x components, well, there is no x component, so there's no x reaction. Sum of the y components, work it through, and you get a formula. Because we've got two unknowns, RA and RB, and then use some of the moments about A first, and we find that that cancels out the RA because it goes through that point, so we can figure out RB is 12.5. Should have really had some units in there. So let's stick them in now. Kilonewtons, and that lets you figure out RA because you can take this and stick it into that one. So RA is 7.5 kilonewtons. And then I'm just checking it by checking the moments about B. And so figure out all the moments about B, check it all adds up to 0. And I actually made a couple of mistakes, so I fixed them. But it's only because of doing this check that you find those little mistakes. Should really underline my free body diagram. So we found the supports, and now we're going to draw the shear force diagram. And so we could just draw this, well, I'm just going to do the section thing again. You could just draw it from the little rules we've learned about following the forces. And then there's another little rule, oops, let me just copy it down so I can see what I'm doing. There's another little rule that these concentrated moments, the couples or the pure moments, they don't affect the shear force diagram. They do affect the reactions. And so the shear force diagram starts at a different place because this reaction will change because of this moment. But the shear, as you come along here, you don't have to do anything with that moment here. The shear force diagram just ignores it because the forces in a pure moment cancel each other out, so it doesn't affect the shear force. But what I'll do is I'll just quickly draw some more sections. We'll just look at what's happening as we go along this beam. What I'll do is I'll take a section just before a force and just after a force. So each segment, you could call these segments of the beam, between the forces or the point loads or whatever, each one is a segment. And because they're all point loads, the shear force is going to be constant between these segments. So we'll just look at a little segment just before and just after each of these point loads and check what they equal. And then we'll just draw the shear force diagram using the kind of quick rules. So let's do that now. Back in a minute. So I've drawn each of these sections, so starting from this side and going this way. Let me just move this one across a little bit. Just before I keep going, I'll just go back. In the previous example, there's something I forgot to do. And so I was just using the scale here. This is 3 kilonewtons, the shear here. Often, well, you should definitely write 3 there. To do it in proper size pen. 3, this is V in kilonewtons. Sometimes people write it along the line as well, so 3 kilonewtons, like so. But I've forgotten to do that, so go back and do that now. Okay, so back to this one. So where were we? So you see, once you add a few forces, it starts to get a bit more time consuming to get through it all, especially if you were to use method of sections to figure all of this out. And that's why we look for these quick rules. But let's use method of sections just so that we can see what's going on. That there has somehow turned it black because I'm a numpty. Turn this one back to red as well. So in all cases, what we're doing is the sum of the forces using the normal. Oh, first of all, I've drawn on VA. That's where you've split it and you've turned it into an external force by cheating or by cutting it. Imagine cutting it, and you've decided to draw that down the way because it's on the right hand side, and for positive shear, that force should be down on the right hand side. Okay, so just remembering that. But once you've done that, you go back to normal directions for different signs. And so you just be saying, well, look, to find that VA, we're going to use the sum of the y components adds up to 0. But another way of thinking that is you can add those up and then take it to the other side. And so what you can do is you can add these up and then take the negative, and you'll get what VA. Let me just have a think about that for a minute. You can add them up, and that's what VA is. Let's just do that, actually. And so the sum of the y components must be equal to 0. Therefore, we're going to have 7.5 minus VA, because it's going down the way, is equal to 0. And therefore, VA equals 7.5. So rather than writing that out each time, we can just notice that VA is just the sum of the other forces, because it's been done negative direction this way, because you're getting a positive shear deformation, a positive internal shear force means that VA is down on the right hand side. And therefore, when you sub that into Fy, you get this. And so therefore, this force here is just the sum of the other forces. So what we're doing here is we're saying, look, we're going to take a section just before that 10 kilonewtons. So it's at 2 meters, so maybe like 1.999 meters or whatever. And what would you get for VA if you did that? Well, it's 7.5. And so you're going to go up 7.5. You're going to come along until you get to 10. It's still going to be 7.5. But as soon as you cross over that 10 kilonewtons, you've now got plus 7.5 minus 10. So that's going to be minus 3.5 kilonewtons. So then this is going to, 2.5 kilonewtons. So this is going to drop down to minus 2.5 kilonewtons. Then we're going to keep going along until we get to just before that 5 kilonewton upward force and the pure moment of 10 kilonewton meters. And all the way up to there, it's still the case. You've got 7.5 up, 10 down. Therefore, you're going to get 7.5 minus 10 minus 2.5 is just going to be equal to VA minus 2.5. So VA is actually up this force is really up the way. You've actually got negative shear. But 7.5 minus 10 minus 2.5, so you've got a shear of minus 2.5 right up until you get here. So that was the same as this one because nothing's changed because you've got no new forces. But once you get past that 5 kilonewtons and 10 kilonewton meters, as soon as you get past that, so maybe 4.001 meters, then now we're going to have 7.5 minus 10 minus 2.5 plus 5. So it's going to be plus 2.5. This pure moment changes nothing. This changes nothing because there's no net force associated with that in the y direction. And so you just go straight past pure moments. As I said, they matter for finding the reactions. It changes these reactions if you put a moment in there. But it doesn't affect the shear force diagram because it doesn't have a y component of force. So we've gone along. I should really write these down. So this one here, and you can work through the calcs if you're not sure where I'm getting these numbers from. Just do this up here. just do the sum of the Fy, just do that thing. So up until that point, VA is going to be 7.5 kilonewtons. But once it gets to here, it's now, I'll just write it out, VA, so now you've got a 10 kilonewtons downwards, so now it's going to be minus 2.5 kilonewtons. Keep going along, 3.999, nothing's changed. You've still got plus 7.5 minus 10, so VA is still minus 2.5 kilonewtons. But as soon as you go past that upward 5 kilonewton force, it changes. And so VA is now, so it's all of these, 7.5 minus 10 minus 2.5 plus 5 plus 2.5 kilonewtons as the shear as soon as we get past that 5. Then it stays the same all the way up to 6. All the way up to 6 stays the same because you haven't added any other forces. But as soon as you get past 6, you've got a downwards 15 kilonewton force now, so it's going downwards. So if you were to add all of these up, you get 7.5 plus 10 minus 2.5, 2.5, take away 15, VA is going to be equal to minus 12.5. So far so good. Then till we get just before the support, nothing has changed. So VA is still minus 12.5. But as soon as we get to that support, I haven't actually forgot to actually draw it on, but you're going to have a reaction. And the reaction was 12.5. Just get the right color for a reaction. Sorry, the reaction was 12.5 positive direction. So 12.5 kilonewtons, that's what we'd calculated for the reaction before. Let me go back up, it's here. And so we're going to have minus 12.5 plus 12.5. Therefore, our shear force is now going to be 0 kilonewtons. Kilonewtons. Okay, so we could have used the method of section and just checked how it changes as you go along, but quicker just to draw it. Always keeping in mind why it works. And so it's that stuff I'm going through that explains why it works. So what's the minimum we had? Minimum minus 2 minus 12.5. The maximum we've got 7.5, I think. Okay, so I'm just thinking about what scale to use, so I'll do 5, 10. So minus 5, minus 10, minus 15. It's going to be my shear axis. This is going to be my distance axis. We need to come along 8, so that might be 2, 4, 6, 8. So this is x in meters. This is shear in kilonewtons. And so like we say, so the rule is you go along, when you see a force, you follow it. So we've got 7.5 kilonewtons upwards. And so we're going to go up 7.5 kilonewtons. And it's going to stay like that until we get to the next force. The next force is 10 kilonewtons downwards. So we're at 12.5. Sorry, we're at 7.5. And that's why you should write it on. So let's just write it on. 7.5 kilonewtons. Then we're going to go down. And we're going to take away 10 because it's going down 10, down 10. So that's going to get us to minus 2.5 kilonewtons. Then it's going to go along until it gets to the next force. Then it's going to go up 5. So it's going to get to 2.5 kilonewtons. Then it's going to keep going until it gets to the next force. And then it's going to go down 15. So that's going to take us to minus 12.5. Then it's going to keep going along until it gets to the next force. It's going to take us to there, and then we're at minus, let me just write these on. So this was minus 2.5 kilonewtons. This one was 2.5 kilonewtons. This was minus 12.5 kilonewtons. And then we're adding on the reaction 12.5 and it gets us back to 0. And that's a way of checking you haven't made a mistake. If it doesn't come back to 0 at the end, at the other support, then you've made a mistake somewhere. Okay, and then we'll just shade that so it's easy to see, or hatch it, sorry, not really shading it, hatch it. So it's easy to see where it is. And we should probably put in a title. If we just want to, I might just ditch these. Let me just move this down here, just to let people know what that is. So this is the shear force diagram. Now I've got one more thing to think about for shear force diagrams, and then we'll have a look at bending moment diagrams. Okay, so keeping in your head that what this is about is it's just at any one point, this is the force trying to split this downwards, like so. It's the force trying to break this beam across the way. Remember, we kind of, what did I show it with? I think I showed shear with a block of plasticine one time. And so you start like that, and then you kind of push up on this side, down on that side, and you end up getting a failure that looks something like that. And eventually it'll just split across there. Okay, so that's a shear. And so this is just a measure of how much shear is going across this beam at any one point. That's what we're talking about here. So the highest shear in this beam is at this end, and it's a negative shear, so it's trying to deform like that. Okay, next one.